In this section, we are going to be taking a deeper dive into something that we mentioned in the previous section, but we didn't go into detail on, and that is the ozone layer. So the ozone layer is a part of the atmosphere that is made up of ozone, which is a chemical composed of three oxygen atoms that are bonded together. So unlike the gaseous oxygen that we breathe, which is just two oxygens bonded together, O2, ozone is O3. And you can see a simple comparison between the structure of these two oxygen compounds here. And the defining characteristic of ozone as a chemical is how unstable it is. So that third oxygen atom will break off from the molecule very easily, and that third oxygen atom is extremely reactive. It will react with most things it comes into contact with, and because of this, exposure to ozone is harmful to humans and living organisms in general because it can react with biological molecules, including DNA, and cause damage to them, which can lead to cancer. So, for this reason, when you find ozone down in the troposphere, which remember is the lowest level of the atmosphere that reaches about 7 miles up from Earth's surface, it's considered a pollutant. But when ozone is found in the stratosphere, and this is where most ozone is located, it actually plays an essential role in maintaining livable conditions on Earth. And we'll talk about that in just a second. But first, where does ozone come from? So, ozone is actually generated in the stratosphere through a natural process called the ozone oxygen cycle. And this cycle begins when UV radiation from the sun hits a regular old molecule of oxygen gas, which remember is just O2, two oxygen atoms instead of three. And that UV radiation energy causes the O2 molecule to break apart into two separate lone oxygen atoms. Then each of those oxygen atoms grabs onto an intact molecule of oxygen gas in the atmosphere, and together they become O3, ozone. And then this ozone will absorb more UV radiation from the sun and break it back down into lone oxygen atoms and oxygen gas, and we end up right back where we started. So you can see how this is a cycle. And as long as the rate at which ozone is being created is the same, roughly, as the rate at which ozone is being broken down, then the cycle sustains itself and remains in balance. However, that balance of ozone creation and destruction has been disrupted by human activity in recent decades. And that's a problem because the fact that this ozone oxygen cycle absorbs UV radiation as it runs its course means that ozone actually serves as a buffer that protects the Earth, the surface of the Earth, from exposure to excessive levels of UV radiation. So, a little more about UV radiation. As we mentioned in the last section, there are actually three different types of UV radiation that the sun produces. UVA carries the least energy and therefore is the least harmful. So, you can see UVA represented in the lighter orange yellow color on the left side of the image. And UVA is not absorbed in the ozone oxygen cycle. So it makes it through the ozone layer and it travels to the surface of the Earth. So this is the type of UV primarily that you're trying to protect yourself against when you wear sunscreen. And when we say it's the least harmful, that doesn't mean it's harmless. It just means that it's not as intense or harmful as the other two. UVB carries more energy than UVA, but 90 to 95% of it gets absorbed by the ozone layer. So we're largely protected from it. UVB is the one that's represented in the darker orange color in the middle. And ozone is actually the only known gas that absorbs UVB radiation. So that gives you a sense of its unique importance. And then finally, UVC is the most energetic and the most harmful. And this is the one that's shown in red on the right side. But thankfully, the ozone layer absorbs virtually 100% of the UVC and therefore buffers the surface of the Earth from exposure to it. So the bottom line is that the sun is throwing out all sorts of harmful radiation, and the ozone layer blocks the worst of it, which makes it possible for life on Earth to carry on. And you can imagine then that the depletion of the ozone layer would represent a major threat to the planet And ozone depletion is exactly what has happened in recent decades over some parts of the planet. And we know this because scientists have been measuring levels of ozone in the atmosphere since the 1920s and monitoring changes. And in 1985, the British Antarctic Survey first reported their data showing that the thickness of the ozone layer over Antarctica was being depleted. So, in other words, the ozone layer was getting thinner. And furthermore, the region in which this thinning was happening was also getting larger. So in this image, you can see a representation of the size of what's referred to as the ozone hole in the same month of September every year between 1979 and 2019. And you can see for how a long time the hole was getting worse and then staying about the same. And then in the past few years, you can actually see the hole is getting smaller. So the healing trajectory that the hole is now on is thanks to environmental protection laws that were passed to stop the human activities that were causing the hole in the first place. So, what were those human activities that were causing the hole? Well, humans were releasing chemicals into the atmosphere that were throwing off the balance of the ozone oxygen cycle, and therefore they were causing ozone depletion. Ozone depletion happens when the rate at which ozone is being broken down is greater than the rate at which it is being created. So, in other words, the ozone is disappearing faster than it's being made. So, here highlighted in yellow, you can see the step that generates ozone from oxygen gas, as we discussed previously. And this is a step that absorbs UVC radiation. And then here highlighted in pink, you can see the breakdown of ozone back into oxygen gas. And this step absorbs both UVB and UVC radiation. And remember how we said that ozone is the only known chemical that absorbs UVB? So if you don't have enough ozone around to absorb that UVB because it's not being generated fast enough, then more of that high energy UVB starts to break through down to the Earth's surface. And this is a problem. So, why was it happening? Well, people invented chlorofluorocarbons, also known as CFCs, and started releasing them into the environment. CFCs are man made chemicals that are made of chlorine, fluorine, and carbon. And here's a little cartoon of one. And they are extremely stable and non reactive, while also being capable of absorbing a lot of heat energy, which made them great candidates for use in aerosol sprays like shaving cream and hairspray. And they were also commonly used as coolants in refrigerators and air conditioners. And because they are so stable, they are also extremely persistent. And when they are released down here on the Earth's surface, they remain intact, they don't break down, they swirl around in the troposphere, and then eventually they make their way up to the stratosphere. And then once they're in the stratosphere, they get exposed to UV radiation. And although they are extremely stable, the UV radiation is enough to break them apart. So the chlorine atoms will break away from the rest of the molecule. And when those chlorine atoms encounter a molecule of ozone up in the stratosphere, they will react with it and pull off one of those oxygen atoms. This effectively destroys the ozone and transforms it into oxygen gas, which then removes the opportunity for that process to occur in a way that absorbs UVB radiation. But what's even worse is that this chlorine atom won't hold on to that oxygen atom. It will drop it off on another free lone oxygen atom, which effectively creates another molecule of oxygen gas, and also frees up the chlorine atom so that it can keep doing this process over and over again. So the effect that a single chlorine atom has is multiplied astronomically. One chlorine atom repeats this process and destroys about 100,000 molecules of ozone, which results in the phenomenon that we call ozone depletion. And again, without all of that ozone, more UVB radiation breaks through and reaches the surface of the Earth. The last question we need to address is why the heck this process was specifically happening over Antarctica. Well, Antarctica has some unique conditions that make it more susceptible to a high concentration of ozone depletion. So, in the winter, air obviously becomes much colder and therefore denser over Antarctica. And this creates an area of high pressure that gets isolated from the air in lower latitudes that experience more mild temperatures. And within this high pressure area, a polar vortex forms, which circulates the air way up into the stratosphere. And normally we said that the stratosphere doesn't contain any water vapor, but the polar vortex drives ice crystals way up into the stratosphere, where chemicals like ozone and chlorine and others will attach to the surface of those ice crystals. And the surface of the ice crystals creates an opportunity for those chemicals to come together and react with each other. And furthermore, as ozone becomes depleted, the polar vortex keeps the air over that region isolated above the Antarctic and prevents it from blending with the air that's at higher latitudes. So, this keeps the phenomenon concentrated and amplifies it in this specific area. So, in other words, ozone depletion occurs at an accelerated rate over Antarctica because the air remains concentrated there. And therefore, Antarctica served as a sort of canary in the coal mine. It was like a pre warning sign of what was coming to other regions of the globe if these chlorofluorocarbons, these CFCs, continued to be used and released into the atmosphere. Fortunately, Antarctica is not an inhabited region, but the amount of UVB that was getting through the hole in the ozone layer over Antarctica would have caused a substantial increase in the incidence of cancer if that hole were located over a populated region. And it would also have seriously damaged plants and important marine producers like plankton and algae. So, recognizing the threat and knowing what was at stake, the international community banded together and passed this treaty called the Montreal Protocol in 1987. And the Montreal Protocol was a plan to phase out production of CFCs, and it had nations agree to cut CFC production in half by the year 1998. There have been several follow up agreements since the original 1987 treaty that focused on advancing more cuts and also including other ozone depleting chemicals in the treaty, such as halons, methylchloroform, carbon tetrachloride, and hydrochlorofluorocarbons. And the treaty has been a success. And at this point, most countries have phased out production of these ozone depleting chemicals. And as a result, the ozone layer is slowly being restored. All over the world, ozone levels in the stratosphere are rising and restoring the thickness of the ozone layer. And that area where the depletion was the worst, that quote unquote hole over Antarctica, that is projected to recover to conditions that are on par with the year 1980 by the year 2066. For the US's part, compliance with the Montreal Protocol has taken the form of an amendment to a piece of legislation called the Clean Air Act, which we'll talk about in more detail later in this chapter. But this amendment requires the EPA to create programs that end the production of ozone depleting substances, ensure that refrigerants and halon fire extinguisher agents are recycled properly, identify safe and effective alternatives to ozone depleting substances, ban the release of ozone depleting refrigerants during the service, maintenance, and disposal of air conditioners and other refrigeration equipment, and require that manufacturers label products as either containing or made with the most harmful ozone depleting substances.